Hello, everybody. This is Dr. Ross coming at you live from the bridge of the Starship Enterprise. And I'm going to make a quick video about density. The rationale for making this video is because typically you will be taught and be given questions in a textbook about how to calculate density, but seldom insight into what density really is. So similar to the temperature video, I thought I'd throw a few notes together, maybe deepen your understanding a little bit about density and how important it is, despite how trivial it seems. So density is incredibly powerful if we just scratch below the surface a little bit. So without further ado, I'm going to share my screen, and I have a document ready to start annotating over. And I've made some notes to keep me on topic and not ramble about random things like Star Wars episodes or what have you, or Star Trek episodes. Okay, so density. We know from an early chapter in any course that density is an intensive property. So let's see, density is an intensive property of matter. So similar to temperature, which we already made a video about that, it's an intensive property, which means it's independent of sample size. So density is independent of sample size. Okay, density has an equation, so I'm going to call it lowercase d. Density, lowercase d, is mass P in a volume. Okay, so it's mass P in a volume. What else do we know about density? Because density is an intensive property, so because it's an intensive property, density is a constant. Because, so why is anything a constant? Well, additions and subtractions must exactly match and therefore negate each other, right? Cancel each other out. So the way to phrase that in a slightly more sophisticated way are sources and sinks. So we add from a source, we take away from a sink. So sources and sinks of mass are equal. So here specifically, I'm talking about mass density. I could be talking about other types of density, but here, until specified to the contrary, we're talking about mass density. So the sink and source of mass is equal. We can write that in symbolic language. So we can write sources and sinks of mass are equal in symbolic language by saying that we can actually write it properly if we take care. We can say that the sum over all objects I of the sources and the sinks that are labeled I are equal to 0. So that's how you would write it symbolically. So we take all of the sources. If there's 2 of them, you could have source 1 and source 2. If there's 8 sinks, you could have sink 1, sink 2, sink 3, sink 4, sink 5, etc. through sink 8. But rather than have a bunch of little numbers in here, you say, okay, whatever your label is, I'm gonna call it label I, where I can be any number. And then wherever I see an I add them together. So that's the nice abbreviation used here. Okay, so far so good. There must be a connection between density and conserved quantities. Why? Because we've just said that density is a constant. That means it doesn't change. At least the mass density in this context that's going to be useful for chemistry is a constant. So there has to be a way to describe it as a conserved quantity. So we're going to start to use the language of conserved quantities, which is a generic language. So there must be a connection between density and conserved quantities. And there is, but the devil's in the details. What do we mean by a connection? Do we mean an exponential link? Do we mean a correlation? Some other type of polynomial? So what do we mean by connection? I mean, pretty much everything that has a connection, whether it's connected or not. So the devil's in the details. For now, I'm going to say it's a reasonable, but a slightly more complicated than you might expect connection. There is a connection. So we said there must be. We look and we see that there actually is. There is a connection. But it is more complex than initial inspection would indicate. It is more complex, not too much more, than an initial inspection would indicate. Okay, and I'll feed you through that initial inspection, and we'll see that it's a bit more complicated in a few minutes, not right this second. Density is a vital component of a continuity equation. So I'm going to introduce you to basic continuity equations. Density is a vital component of a continuity equation. So what on earth is a continuity equation? Anything that's conserved and typically is transported, so there's a constant transportation of a property, has a continuity equation. So imagine you're working in a fulfillment center, and you're on a production line, and your job is to make sure there's a steady flow of envelopes for whatever reason. That's a transportation, so it applies to continuity. You want a nice steady flow, so I want one envelope, one envelope, one envelope, one envelope. If I look and there's always the same amount of envelopes, that's a conserved amount of envelopes, and it would have a continuity equation. If I look and there's one envelope, 10 envelopes, 3 envelopes, 1 envelope, that's not conserved, that's changing. Now you could still have a continuity equation to measure the fact that it's changing. Density won't be changing in our example today, but anything that is being transported, you could apply a continuity equation to and see if it's conserved or not. Okay, but I'll give you an example of a continuity equation. For now, we're just introducing some language. So you don't know what a continuity equation is yet, but you know that it's important enough to keep watching, hopefully. Density actually not only appears in a continuity equation, but appears twice. That's how important it is. So let's have a look. Let's have a look in black ink. density appears twice in a continuity equation. And in two different ways, that's why it's not just once. In two different ways, which kind of is redundant because of course it's two different ways it appears twice. But I will add it anyway. So to give you a feel, and then on the next page we'll go into a bit more detail, we're going to have the change per unit time of the density, and that'll be one instance that you'll see it, and then we'll have the change per unit space. Of the density. This is how it's going to appear. Now, compare this with the previous video that we looked at, which was temperature. So I'm going to write this in red, and I'm going to say compare with temperature that's in another video. Can't write and speak. I was thinking density, but I said temperature. But I was thinking density, so I wrote density. Compare with temperature, which is in the temperature video. And we said that that was a change in heat. I think was the exact example I gave. But in general energy, but we can use heat here, with a change in time. And we said that that was proportional to minus a temperature gradient in space. So not identical, but definitely enough similarity to remind you of it at this point. So the text in red, go back and look at the temperature video and you can have a look at that. But I just wanted to bring this out, this change with respect to time, change with respect to space. We're not talking about space-time here. There's nothing relativistic about this. We're just looking at time and space totally separately. Okay. Okay, so we've got, so going back to the black text, we've got a time component of density and a space component of density. So let's now formally introduce a continuity equation. Now, I'm not going to derive it. I'm going to introduce it and then state it, and then hopefully get you comfortable with it. So let's look at a general continuity equation. Continuity equation. Okay, continuity equations describe the transport of some extensive quantity. We said earlier the density is no, we didn't. We said, that's not right. We didn't say extensive, did we? We said intensive. So let me clarify that as we go along. Continuity equations describe the transport of some extensive quantity. Now, before I totally baffle my audience, remember what an extensive quantity is. It's something that exactly depends on the sample size. On the sample size. E.g., mass. Mass exactly depends on the sample size. Mass is an extensive property. If I give you 1 gram of sugar and then I change the sample size by doubling it to 2 grams, I've changed what I've given you. 1 gram has now become 2 grams. I've scaled the numerator, the denominator had no units, so it didn't scale correctly. So mass is an extensive property. Density is an intensive property. So how on earth can we use a continuity equation for density? Well, remember what we said. We did indeed say that density was an intensive property up here. But then we said somewhere, I don't think I wrote it down, but the density we're talking about here is mass density. Okay. So specifically, I'm looking at mass per unit volume density. So it's the mass that's the property that's being transported. So you can think of it that way. Okay, so I'm going to come back to here, and mass is an extensive property. Okay. Continuity equations are used for conserved quantities, but they're actually a strong version of a conservation law. Now, so far in this present course that my students are in, we haven't looked at conservation of energy yet. So conservation of energy, the way I'll present it to you, is a softer version of a continuity equation. And rather than just bump it on you now, because I really don't want to talk about conservation of energy right this second, I want to look at it, this more robust version in the continuity equation. Eventually, when we look at thermochemistry and we look at conservation of energy, the way I would typically do it, using a softer version, we'll be able to come back and it'll give us a chance to review this topic. So there's definitely a merit to doing a related version of it now and then waiting and then doing another version rather than just do everything at once. So continuity equations are stronger versions of conservation laws. That's what I was saying. Continuity equations are stronger versions. So I'm keeping the suspense about what it actually looks like. Hopefully that's exciting. Stronger versions of conservation laws. So for example, conservation of energy. Conservation of energy, which again, we'll actually mention it in terms of a continuity equation. I will look at conservation of energy, but in terms of thermodynamics, I'm not really going to look at it. That'll be for later, but that would be a softer version. So what do we mean by a stronger version? Well, let's consider the weaker statement. So a weaker version of a conservation law is a statement that energy is conserved. So I guess why is the concept of conservation of energy a weaker statement? Because that's the question. Merely saying conservation of energy, why is that a weaker statement? Because it allows or it permits teleportation. It permits teleportation, which is appropriate. I wasn't thinking about that when I picked my my location for this evening, but it's appropriate. They have the teleporter in Star Trek. Does that mean the Enterprise is? I don't know. There's probably run-ons, and I probably shouldn't use the word Star Trek. But anyway, because it permits teleportation. So, for example, you can state in a weaker state. You can give a weaker statement that says, "In the universe, energy is conserved," but then right in front of you, all energy disappears, and you're like, "Wow, that's weird. Where did it go?" Well, I didn't tell you that it teleported to the Andromeda Galaxy. Go check it out. It's there. Well, I can't because I'd have to travel at the speed of light to get there, and that would take a long time. And I'd had to travel slower than the speed of light because I have mass, but that withstanding, it'd take me a long time to verify. So for all I know as a scientist, that energy disappearing in front of me is evidence that there's no such thing. Well, that's because your statement was weak. The continuity equation builds in or it prevents any teleportation occurrences because it looks at local conservation, which if anything were teleporting to the Andromeda galaxy, that wouldn't be local, right? That would be distant. So continuity equations don't allow teleportation. Continuity equations don't allow such teleportation. Of energy in this case, because we're looking at energy, since energy can only move via continuous flow. Can only move via a local continuous flow. Okay, so cast your mind back to that conveyor belt, the fulfillment center, where you're looking at those envelopes coming across. The weakest statement, conservation of envelope, would be, okay, there's envelopes here. Oh, they've suddenly disappeared. Oh, that's because they went into the other fulfillment center that you can't see right now. If only you could, you'd realize that everything's okay. Well, that's a weak statement. Easy to run into issues. But the continuity equation, because it looks locally, it says, okay, look in front of you. Tell me if you notice anything change. No, I didn't. Okay, then it's conserved. So that's why it's a stronger statement. Okay. So we're getting 30 seconds away from actually writing the continuity equation. But one more tease. The weaker statement is our conservation of energy. And we can write that as the change in energy per unit time is 0, right? So energy, if it doesn't change per unit time, then it's conserved. So that would be a weak statement. Nothing in that equation remotely linked to teleportation. And that's what we said, right? That weaker statement doesn't have that in it. So how do you put a teleportation caveat into your equation? So here's the strongest statement. Here's the strongest statement. And then I promise, link it back to density, because the whole point, I didn't call this a continuity equation video because nobody would watch it that way. I called it a density video, so I'm going to drag it back to density in a second. So the strongest statement is not just conservation of energy, but it's local conservation of energy. And our equation is partial of u. I'll define what these terms mean in a second. Partial of u over the partial derivative of t. That is going to be similar to this. So I haven't called it E, I've called it U because it's not an energy, it's an energy density. But essentially that U is going to be our density. And it's partial because there's another part, and I basically mentioned what partial meant because we had a partial derivative in the temperature video. So this is not a video on partial derivatives. I have another video if you want to look at that on partial derivatives, just give you a feel of how to use them. For now, the D just means change. The curly D means a partial change because there are other parts that to be considered separately. So here's the teleportation symbol. It's a funny upside down triangle that we call del, and I'll write that in a second. And then Q equals 0. So that's our continuity equation. So there's a big fly buzzing around. So this is the layout of a continuity equation. So A continuity. And let's define some of these terms. So U is energy density. So there's our word density. It's not a mass density here, but it could be. Density doesn't have to be mass density. It can be anything. Anything that's flowing that has an intensive property that flows. A continuity equation, U is the energy density. So here it's energy per unit volume. Okay. Q is the energy flux. So I'll explain what flux is in a second. But it has units of energy per unit area per unit time. So energy per unit area per unit time. Scroll down a wee bit. So energy per unit area per unit time. And this thing del, so this symbol is called del. And del with a dot, the dot product, so del, it's called del dot, is the divergence. So divergence means exactly what it says. Divergence means something that's diverging, spreading out. So if you drop a pebble in a swimming pool, the ripples of water would diverge from a point source. So if you see energy coming away in all directions, if you swim against the flow and you try and find out where it's all coming from, you'll find a point. That point is the source of divergence. So, okay. Just a little, I don't know if I've done it on the next slide. I think I have. Oh no, it's on the next slide. I was going to tell you another way to think of flux, but it's on my next page of notes. So anyway, so we finally got this continuity equation. Just let me double check. I am still recording. Yes, I am. Very good. I had my computer make a noise and I had a horrible feeling I'd press stop. Okay, so we're still on the Starship Enterprise, still recording. Very good. Okay, so we've got this continuity equation. Before I move on, I just want to say, so we've got density in there, right? I've definitely got density in the U term because we've said that is, actually I will write it here. We've said we've got density in the U term because this is a density video. I've got density locked in that flux. So actually I'll put it in red over here. So Q is flux, or energy flux, sorry. Q is the energy flux. Another way to think of the energy flux is density, in this case, energy density times by field velocity. So it has units of energy density and velocity. So both terms, the term on either side of the plus sign, have density. Both terms have density. So I just wanted to point that out to you so you don't think I'm cheating you talking about flux. This is definitely a density video. And just to convince you that the units make sense, if we just look at the units, we'll return energy per unit area per unit time. So the density here is going to be, the energy density is going to be, numerator is going to be energy per unit volume. That's the energy density. But then we've got velocity. What are the units of velocity? The velocity are, for example, meter per second. So meter is a length. And we've got reciprocal time down here. So length over time, they would be the units of velocity. So length here, remember velocity is length cubed, so we can replace volume here with length cubed. So the length here is going to cancel one of those lengths out, so we get energy per length squared. Length squared is just an area, and then we've got time. So we get back to this unit here when we talk about energy flux. But because this is a density video, then you can just think of energy density by velocity as the flux. Okay, so I believe at that point as much as I need to. So let's move on to, let's move on. Okay, so here's a question that we should ask. Why does density appear twice and in two different ways? So why does density appear in the weakest statement? So remember the analogy with the weakest statement. So we've got this weaker statement here, this apparent change with time, but then we've also got this divergence. This is the teleportation. So are you constant? Yes. Are you flowing somewhere locally? No. So that's that extra teleportation term. So why are there two separate terms? And we've kind of qualitatively answered it already because I want to make sure there's no teleportation. But I want to give you a visual interpretation of this as well. So the question is, why does density appear twice and in two different ways? Two different ways in a continuity equation. So think continuity, continuous, conservation is continuous. So why does it appear twice and in two different ways? Well, to answer that, it's going to take a sweet second, so let's start. Let, in general, instead of energy density, instead of energy flux being Q, let's give it generic flux J. So let flux equal J. So just a generic flux. And let's say this specific one, rather than energy, which I called Q on the other page, let's call it J, and it's going to be a regular mass flux. So let's say that this is mass per unit volume rather than energy. Sorry, not mass per unit volume. Well, mass per unit volume times by velocity. So we can cut that out and say it's mass per unit area per unit time. Mass per unit area per unit time. So let's actually write that out in full. So let's say it's mass per unit area per unit time. So we can say that that is density times by velocity. So mass per unit area per unit time is density by velocity, exactly the way I've shown here. So here we had energy per unit area per unit time is the same as energy per velocity. I've erased it now, but if you go back a couple of minutes in this video, we explained that the units cancel and et cetera, et cetera. Okay, so we're just reminding each other that the only change here is I've got mass rather than energy, just because it makes more sense with my diagram. It's easier for me to say, look at this piece of mass. It's very hard to say, look at this piece of energy. So when I was making my diagram, I had to swap it out. Okay, so here's the visual that hopefully will make this more concrete for you. So I've got, it's ultimately going to be a cylinder, and I've got 5 pieces of the cylinder. It's like a tube. So I'll do the dashed line to show you that this is a tube, and I don't want to do a hard line. I just want my cylinder, I want to focus on these snapshots along this tube. Okay, so consider a two-dimensional, consider two-dimensional slices through a tube. Consider two-dimensional slices through a tube. Slices through a tube. Okay, so that's what we're looking at in my little visual to the left. Okay, consider two-dimensional slices through a tube. And we're going to number them 1 through 5. So slice 1, slice 2, slice 3, slice 4, slice 5. And in each one, I'm going to put a piece of mass. Slice 1 has 1 piece of mass. Slice 2 has 2 pieces of mass. Slice 3 has 3 pieces of mass. You guessed it. No surprises. 5 pieces of mass. And this is why it would have been really awkward to talk about energy. So I had to swap it out for mass. Okay, reading left to right. Okay. So reading this visual left to right, the divergence of the flux, remember in our continuity equation we had divergence. Well, here the divergence of the flux is positive, since the mass in each two-dimensional slice is increasing. Since the mass in each two-dimensional slice is increasing. From 1 to 5. So you look at slice 1, there's 1 piece of mass, slice 2, 2 pieces of mass. And as you go along, there's more and more and more. So this divergence here, this del dot J, we saw that in our continuity equation where we had del dot Q, where Q is the energy flux. Here we've got a mass flux, which I've called J. But the idea is that this mass is diverging. Okay, so hopefully that's straightforward. Let's look at reading the other way. So reading from right to left. Reading from right to left. You can probably guess that the divergence is negative, since the mass of each two-dimensional slice is decreasing. Since the mass in each two-dimensional slice is decreasing. From 5 to 1. So going to right, 1 through 5, going right to left, 5 through 1. Change direction, you change the sign of the divergence. We don't say, I don't even know what the opposite of a divergence is. We don't say the opposite word, we just say a positive divergence or a negative divergence. So we have a positive and a negative divergence respectively. Okay, that's fine. But there's another way to inspect that diagram. And if that were the only way to inspect that diagram, we'd only need 1 instance of density. But our question is, why are there 2 instances of density, which was our initial observation back in the day when we said density appears twice in the continuity equation, but we're finally explaining that now. Okay, so let's move on. Let's look at another way to interpret that same diagram, and this is why you need another consideration. So let's look at the diagram again, and we can interpret it slightly differently. So here's our 5 slices through the same tube. But now, so you know what it is, consider 2-dimensional slices through a tube, but let the shaded region be a 3-dimensional volume. So instead of looking at slices, instead of looking at slices and ignoring everything else, now I'm ignoring the slices and just looking at everything else. So let the shaded region, and if I combine these two, I have everything, right? So there's only two instances of density. Okay, so let the shaded region be a 3-dimensional volume of the tube. So this is our new way to interpret the tube now. So I've got the slices just to show you that they're still there, but I'm going to ignore the slices. Here they are, but I'm going to ignore them. So my original slices are there, except 5, which was drawn in the wrong place. But I'm now interested in the shaded region between the slices. Ah, never saw that one come in, did you? So had I said interpret the diagram, some of you might have looked at the slices. Some of you might have looked at everything except the slice. But if we look at the slices plus everything else, that's the plus in our continuity equation. Anyway, okay, without further ado, let's annotate this a little bit. Let's start on slice 1, and let's look what happens when we end at slice 2. So what happened in the middle is we gained 1 piece of mass. Start on slice 2, we end up at slice 3. What happened in the middle? We gained 1 piece of mass. Going from 3 to 4, we gained 1 piece of mass. Going from 4 to 5, we gained 1 piece of mass. So going left to right, we gained 1. And as you might anticipate, going right to left from 5 to 4, we lost 1. 4 to 3, we lost 1. 3 to 2, we lost 1. 2 to 1, we lost 1. Going right to left. Okay. So that was our alternate way to interpret this. So let's comment on that. Reading either left to right or right to left a little bit of space here. So reading either left to right or right to left, the change is the same. So the rate of change of density is constant. It's either +1 or -1. Thus, the change in density, which I'm going to call the symbol rho, per change in time is 0. So here, RHO is this symbol here, and this is our density. Why have I lost my partial derivatives? Because I'm not looking at the slices now. That was the other part. I'm just looking at one thing, so I've got my regular derivatives. The density is not changing here, right? With time, if I inspect the shaded region, the density is always the same because I'm ignoring, oh, sorry, not the density, the change in density is always the same. The way the absolute density is changing is fixed. So I've got essentially the same increment of change in each section separated by these slices. Okay, so you can pause this video and have a think about that. You probably do need to think about it a little bit. I think me just repeating the same thing is not as useful as you having a think. So let's make some conclusions about what we've just seen. So we saw that change in density rho per change in time is 0, while the divergence of the density flux can be plus or minus. So we had two different ways of looking at it, and we got two different outcomes. Both of these pieces of our continuity equation contain density. We've got density in the first term, and then we've got density flux in the second term. But they give us different answers, so we have to consider both terms. If they gave us the same answer, we could probably neglect one of the terms. But the fact that we can get plus or minus 1 and 0 in the same, by inspecting the same diagram, means that we have to inspect both parts of the diagram. So hopefully, you know, that makes a bit more sense when you've had a chance to look at it. Okay. Let's consider another diagram. So maybe it's always like that. Maybe it's always 0 and plus or minus 1. Well, if I can show you one example where it's not, this validates the reason why we have to be careful. So here's the one example where I can get other results. So here's our familiar tube again. And we don't have that much longer in this video, you'd be pleased to know. I appreciate the longer video, the less likely people are going to watch to the end. I hope not, but maybe I'll keep the best part till the end. I don't know. But these things are tricky. They take, you know, you have to go slow. They take a few seconds to get into it, get into the meat and potatoes of the argument. Let's say that's our tube. I won't say what it is because you've seen what it is by now. But now we've got a piece of mass. We've got two pieces of mass. Now we've got 3. Everything looks the same as before. But actually what you don't realize is I'm following a Fibonacci sequence. So this next one is going to be 5, not 4. Ooh, mystery. Mystery if you're watching this video this long in, mystery. This one's got 8. 3, 4, 5, 6, 7, 8. Even more mysterious. So I'd encourage you to look up Fibonacci numbers. It's really cool. Not part of our course, but definitely something you should be aware of anyway. So we've got this Fibonacci sequence that is not linear. So it's a different scenario. So let's have a look. So here, reading left to right, we've again got a divergence that's positive, and we have to the left is negative in the opposite direction. So that's the same as before. Okay, so same as previous example. Okay, however, the change in density, oh, sorry, the change, don't need partials here. The change in density over time is positive, and that's a new discovery. It's not zero. It was zero in the previous example. Reading left to right, and delta rho per unit time is negative in the opposite direction. So let's have a look at that real quick. Should get a little bit quicker drawing these diagrams now. Not that much though. Okay, there's our tube. Continuous tube. We've got our 1, our 2, our 3, our 5, now 8 pieces of mass. Okay, and just like last time, I put the last one in the wrong spot. Okay, again, we're just looking at the shaded region now, so we're looking at density. Looking at these shaded bits, not the slices, so the 3-dimensional shaded bits. And going from 1 to 2, we increase by 1. Going from 2 to 3, we increase by 1. Going from 3 to 5, boom, we increase by 2, different, so we need an extra term. Going from 5 to 8, we increase by 3. That's different. Vice versa, you've got -3, -2, -1, -1. Okay. So last couple of comments about this video. So reading left to right, the rate of change of density is not a constant. So d rho by dt is not equal to 0. It's either positive, well, it's positive in this case. Thus, we must consider both instances of density in a continuity equation because they say different things. Both instances of density in a continuity because they say different things, as we've just hopefully demonstrated. Because they say different things. Okay, so hopefully I've tried to make that as clear as I could. Only you can tell me if I succeeded. So just to overview real quick, I wanted, the whole purpose of this video was to give you something a bit more than here's how you calculate density, you know, goodbye density forever. I think if that's all we do, I think we lose how important density is. So I've linked it in intimately with conservation of energy in a strong statement way by introducing how density fits into the continuity equation. So that's going to be a theme moving forward in our course for sure. It all started by stating that there's two aspects that density appears in this continuity equation, a time aspect and a space aspect. We slowly introduced the continuity equation. We could see here that the time aspect of density comes in as the energy density on the left of the continuity equation here. And then in the divergence part, this was the space, the flux, the divergence, the space component here. And we said why you have to have both, or we stated that you have to have both. And then we spent some time, hopefully it wasn't too painful, showing you why, or a way to think about why you need both. You know, why not just have density feature once? Well, you can make, from a pretty simple pictorial argument, different outcomes emerge depending on how you think about density. So hopefully we showed you that. And so we concluded that that's why it wouldn't be enough information to just mention density once.